Welcome back to another video of the complete Java Data Structures Algorithms Bootcamp. In this video, we will be learning about searching in matrices. So like if you're given a sorted matrix, how do you search in that? And how do you reduce the search space? How do you apply binary search in it, for example? So all these questions we'll be doing. And also, since this is a complete bootcamp, so we are covering the entire bootcamp from scratch. No prerequisites are required. So make sure you check out the playlist link in the description below. You will find all the lectures over there for free. And if you want to learn about the assignments and notes and all the code that you want to see, the link for that is also in the description. Before we get started, make sure you pause the video and subscribe to the channel if you haven't already. We do some amazing work on the channel, and we're going to be bringing such nice content to you regularly. Cool. So let's get started. Already covered in a 2D array, something for example. So if you're not aware of what are 2D arrays and all these things, make sure you check out the links in the description. So we're talking about searching in a 2D array, right? So if you're given a simple array like this, you're given an array, let's say a 3 by 3 array. You're given elements like 18, 9, 12, 36, minus 4, 91, 44, 33, 16. And you're saying that, okay, this is a matrix that is matrix given to you. And the target element that you need to search is equal to what? Let's say 91. You need to search whether 91 exists in this array or not. How do we do that? It's very simple. This is not sorted. It's just like random numbers. So you keep checking one by one. You run a nested for loop. Again, if you are not aware of the nested for loop and how to traverse, how to basically run through a 2D array, pause this video, check out the link in the description below. There's a section on arrays. There's a separate video on arrays. In that we have covered the 2D for loop. Check that out. There you will understand how each and every element is. You're going through it and never skip anything. Everything that I say. So array on the equal to target, it will come up. Okay. So this is a very simple search. And what is the worst number of steps it's going to take? Equal to, because we've already did row 1. So if you look, or if you look at any column, that will also be sorted. Take any row number. This is 0, 1, 2, 3, 0, 1, 2, 3. These are the columns. These are the rows. Take any row, it will be sorted. Let's say row number 2, 28, 29, 37, 49, sorted. Let's say column number 3, 40, 45, 49, 50, it's also sorted. Okay. So now you need to search an element in this. Let's say you're trying to search, let's say target element, try to search for 37. Try to search for 37. How are we going to do that? Let's see. So the very first solution that comes to our mind is this similar one. We can do something like this, and then we can search for 37, O of n squared. But the thing is that this is not efficient, and we are not really utilizing what has been provided to us. For us, they have provided that the matrix is sorted. So that is something we have not thought about. So in this case, what we can do is, when you're given such large search spaces, try to figure out how you can minimize the search space. This is also a very nice pattern or a hint in coding interviews that you will get. So if they're asking you to search something and there's a little like a bigger data or whatever, try to see how you can minimize that search. Try to see how you can minimize that search. For example, if you're trying to search for 37, okay, trying to search for 37. So here, what are the few cases when you try to search? So we always look for cases. Let's try to see how many cases we can get over here. So let's say you try by, let's say normal thing that you were doing before. Let's say I try to do this only. Okay. Let's say I try to do this only. I can start by searching like this. Normal. Okay. So whenever I am comparing a particular element with my target element, what are the cases that I can get now that it's a sorted array? The first case can be case number 1. Think about it. There can be as many cases, as like there will be. So let's try to figure out how many cases can be there. So trying to search for elements. So for example, let's say you're trying to search for something like let's say you're at 34 or whatever. Okay, so if the given number, the target number, is actually greater than the number that you are at right now. Okay, so for example, if you're trying to search for, let's say, if you're at this particular, so you're trying to say, hey, is this equal to target? So in binary search we are doing equal to, less than, or greater than. Similarly, the same thing we will be doing over here. The same concept we will be applying over here. Case number 1 can be, if the element is equal to target, answer found. Case number 2 can be equal to what? If the element that you are at is smaller than target, in this case what will happen? It basically means that all the elements that we have in this row of this element, try to see. So for example, if I say if I talk about 25 for example, so here we might do something, and then case number 3 can be something like this. So case number 3 will be equal to that if the element that you are at, that let's say you're searching for, is actually greater than the target. Currently the one we are comparing is actually greater than target. So these were the 3 cases that we had in like binary search also. Okay, in binary search we also had a upper bound and lower bound. Okay, we had 2 places from which we were comparing. So in this case, what all cases are going to compare with it? What is the start and end going to be is my question. Start and end going to be. So in matrix related questions, when you're trying to reduce the search space, you have to think about how you can eliminate rows and columns. How you can eliminate rows and columns. So let's talk about the element being less than target. Okay, so let's say I'm talking about 25 or 29. So is 29 less than 37? Yes, it is. But does it really tell you anything? Does it really tell you anything? Not really. What can you do if 29 is less than 37? Can you eliminate this row? No. Can you eliminate this this column? No. Can you eliminate this row? No, not really. No particular proof over here as such, because it might be possible that it might be possible that there's some other like number over here. So for example, you cannot say something like, hey, 29 is actually less than 37, so all the elements in this column will be less than 37. No, it might be possible that here you had 39 or something, and then you changed this accordingly. Okay, so this is not gonna work. That is why we have to figure out a lower bound and upper bound. The lower bound is obviously going to be this one. Okay, it's the smallest number. Upper bound is going to be in this last column. Okay, so this particular row, this is the lower bound. This last column is the upper bound. So you're going to compare it with which number? Lower bound and upper bound, this one. This is the one you are going to compare it with. So now that we know, let's say the search space has reduced to, let's say we're trying to say this is the row 0 is the lower bound and last row is the upper bound. So let's say the target element is actually, let's say in this case, less than the element that we have, with its comparison. Comparison. So it's saying that okay, 40 is actually greater than the target element, So now we know that, okay, this is the last element of the rightmost element. Does it not mean that every single element in this particular column is going to be equal greater than target? We know that we are, so 2 points, you might be having questions. So 2 points. Point number 1, we are checking the last row. Sorry, we are checking the last column. Okay. So here it's saying that the target element is smaller than this particular number. And we know the target element, let's say, is smaller than this number, and we know that all of these numbers are greater than this number. So does it not mean that all of these numbers are also going to be greater than target element? Hence, ignore this. Means if your element is greater than target element, you can do column minus minus. Now your matrix remaining is this one. Now it will check again. It's going to check, okay, is 30 equal to, greater than or less than the element, like the target. If it's 30 equal to target, greater than target, or less than target, it's going to be like it's less than target, means this one, case number 2. In that case, what will happen? Pause this video, think about it. So if this number is actually smaller than the target number, and we know that all the other numbers on the left hand side of this are going to be smaller than this number, does it not mean that all the left hand side numbers are also going to be smaller than the target number? Hence we can ignore this entire row. Hence row plus plus. Now our search space is reduced to this. Is 35 equal to target, greater than target, or less than target? 35 is less than target. So again, row plus plus, this row will be removed. Now the elements will be something like this particular one. Is 37 equal to target, greater than or less than target? It's going to be like it's equal to target. Okay, answer found. That's your question. That is it. As simple as that. So this is a search column row error column n minus 1. Okay, like the length of the entire like matrix minus 1. So it's like from 0 till n we are running, and let's start the start say matrix and column wise sorted matrix. Take it and index one condition for it. Condition is that okay, or I can the condition is actually less than the length and column is actually greater than equal to 0, 0 equal to target. I can just say found my answer, new integer, and the answer I have found is equal to row comma column. Okay, otherwise I can say that if the matrix, which is the second case, if the element is actually less than target element, so if the matrix of row and column is actually less than my target element, if the target element is bigger, so the target element is bigger, in that case what am I going to do? I'm going to say row plus plus, I'm going to say row plus plus, otherwise I'm going to do what? Column minus minus. That looks good. And if nothing has been returned, it means that it does not exist. So I can just say return minus 1 comma minus 1. That is it. I have an integer array like this. Integer array is equal to, okay, you can also it does not have to be like n cross n. You can just replace this with like m as well. This can also be like n cross m matrix. Okay, so that is basically like the same thing only. N cross here to the matrix. So what it can just put only. Okay, so the only 8, something like this. 9, 10, 11, 12. Just adding simple numbers. 13, 14, 15 and 16. Okay, now in this case what is happening is that array is sorted in a sorted manner. So go like this, then we start going like this, then like this. This is a sorted matrix. Okay, so the question now is that how do we approach this problem? How do we approach this problem? Okay, let's see. In short, what I can say is that what is the pattern over here? If you see that first element of a particular row is greater than the last element of the previous row. Okay, that's why it's like a strictly sorted matrix. So few solutions that come to mind, pause and think about it. First one is like normal search, n square. square or n cross m time complexity. Second one can be convert this into a 1D array, then apply binary search on it. So convert it into something like this: 1, 2, 3, 4, 5, 6, 7, 8 till 16. Then apply binary search on this. You can do something like this, but we are not going to do that. Since we know it's a sorted matrix, let's try to see how we can apply binary search on this particular one. Okay, so in binary search we need the three cases already, right? So greater than, equal to, and less than, right? And we need like lower bound and upper bound. So in the previous example I told you that try to reduce the search space when you're given such a big matrices or whatever. So what I mean by that is eliminating the row, eliminating the column or whatever. Okay, so that is what we did in the previous one as well. Similarly, the same thing we will do in this one also, but the approach will change. Why? Because the array is sorted now. So what we are going to do is we're going to start by numbering the indices. These are the rows, these are the columns. We are going to start by searching on the middle column. You can also start by searching on the row, by the way. Okay, so anyone you can use. Let's say we are searching on the middle column. So as we are trying to reduce the search space, let's see what we can do. So let's take the middle column. As we know the array is sorted, so we will be taking the middle one. So middle column is going to be this one. Let's take this column. Okay, did a little bit. Alright, so we are taking the middle column, and in the middle column we are going to check. Okay, we are going to perform binary search on the middle column. So take middle column and perform binary search on it, because we're trying to reduce the number of rows. You can do the same for rows as well. Take the middle row, try to reduce the number of columns. You can do that as well. Okay, so we can see that, let's say if I'm trying to search for something like 2. Let's say I'm trying to search for 2. Let's say the target is equal to 2. Target is equal to 2. I'm going to perform a binary search on this. So binary search, middle element is going to be 6. It's going to be saying that target element is actually less than the middle element. Target element is actually less than the middle element. So if I know that target is actually less than the middle element, does it not mean that all these other elements are actually going to be greater than the middle element, which is equal to 6? So does it not mean that it will also be greater than the target element? If all of these numbers are greater than, greater than 6 and I know that 6 is greater than 2, does it not mean that all of these numbers are also greater than 2, which is my target element? So can you not say that you can definitely exclude these rows? Okay, hope that makes sense. So case comes over here that if element is actually like again 3 cases. Element, if this is equal to, if 6 was equal to, let's say, target, okay, that way I have found my answer. Okay, case number 2, if element that I'm comparing, if this is actually, let's say, greater than target, in that case what is happening? I'm ignoring the rows that are in between, like up after it. So after this all the rows will be ignored. Okay, cool. So ignore rows after it. And what is the third case going to be? If element is less than target, in that case what will happen? All the rows above it will get ignored. So example, you are trying to search for 10, okay, and you know that 6 is less than 10. It basically means all the above rows above 6 will also be less than 10, and so all the above ones will be discarded. Ignore above rows. That is what we are trying to. This is how we are reducing the search space. This is how we are reducing the search space. So we're trying to skip the rows that we don't want. Okay, in the end what will happen is that only 2 rows will be remaining. In the end only 2 rows will be remaining because only 2 elements will be remaining. Now you may be asking me, hey Kunal, what are the bounds that you are taking over here, right? What are the bounds of the binary search that you're taking over here? First thing that I'm taking is a row, which is going to start obviously from 0. So row is going to start from here, like just like in the previous example. So this is like my, let's say, row start. Okay, this is my lower bound. Upper bound is going to be equal to what? So my upper bound is going to be the last row. So row end. This is going to be my upper bound. Okay, and the middle of this is going to be the middle of this. So this plus this divided by 2. This is the middle. Another case. 2, 3. Pretty good. That is 2, 6. Try to is equal to 3. Then what are you going to do? You are going to consider 4 parts. Part number 1. Part number 2, part number 3, and part number 4. Second point is consider the 4 parts. Consider the 4 parts. Okay. So how do we check for that? Check whether like the target element, which is 3, okay, if it is equal to like any of the middle elements, that's fine. Otherwise you can 1. haven't found, you can just return -1 comma -1. That is in binary search. Okay, what will come mom? Okay, just in a sort, like if arrays videos is done, that constant time. How can we do that? From scratch, see a lot of theory around hash maps and around various ways via which. So what are some of the function? But give me a number. There you go. And so how many sequences can Hey everyone, welcome back to another video, and now we are starting with sorting. So if you're new to the channel, we have started the complete data structure algorithms interview preparation bootcamp. The link for that, the entire playlist, is in the description below. It's completely free. And now we're starting with sorting. So we're going to be sorting the arrays. So we're looking to what is sorting and what are the various ways of sorting. Let's take an example, something like this: 12, 19, 23. Increasing order, ascending order sorted. Bubbles, now I'll sort this in just one. In 3 will come over here, 5, 4 and 2. Now you take the next two elements. Then it's going to be like, hey, is 3 greater than 5? Is the first element greater than the next element? It's going to be like, no, it's not. Then it's going to be like, okay, cool, let's move ahead. Is 5 greater than 4? Yes, it is. Swap. Swap 5 and 4. This becomes 1, 3, 4 and 5. and 2 over here. Now it says it's 5 greater than 2. It's going to be like, yes, it is. Okay, swap it again. This will become what? 1, 3, 4, 2, 5. This is pass number 1. First step. Okay. So this is what we are doing. Why we are doing it? What is happening? Let's see. This throughout our array. Let's see. Largest element. That's true. Similarly, when I run this again with just add AI1 and will come over here. Notice over saying here 4 and 5 going to have this starting the element that is coming over here. Then for a thing is doing, do this. we are going to have an is j greater than j minus 1? It's going to be like, yes it is, swap. After swapping, this will become 1, 3, 5, 4, 2. Then the value of j will increase. Now j will come over here. It's going to be like, hey, is j greater than j minus 1? No, it's not. Then it's going to be like, okay, value of j increase. Is j, sorry, is, when the value of j increases over here, let me just write it in a correct way. So you have I starting from 0 and j starting from 1. So you're just basically going to say that, you know, um, is is j one. Does j have a pointer here? Now no really makes sense. Going to go till about it before for space, right? In opposite. Okay, so for example, you're given an array sorted in descending order, you want to sort it in ascending order, so that is the worst case. Okay, now as I mentioned, forget about what is big O notation right now. This n you can basically imagine as the number of comparisons. Okay, okay, grew like to 4. You can run it for the same the 4 complexity to swap because j is only 5 till 0, and that is how why about it. Okay, the value is this thing, and these are balls. Okay, in the original array you can see in original array in I'll just add that okay, something, and then I can say array is wrong over here. 1 2 3 4 5, something is wrong over here. When I do 1 2 3 4 5, let's say 1 2 3 4 5, okay, it's going to give me 1 2 3 4 5, but the thing is that, see, what is happening over here is the problem is that for I is equal to 0 it will run. Okay, let's try to debug it. Debug. No, did not swap for a particular. Try to find pass number 1. You will see that 5 will come at the end. Come over here, as you can see 1 and 2 are already sorted, so hence it will be like okay for, and yeah. Hey everyone, welcome back to another video, and here we are looking at the second sorting algorithm, which is selection sort. So if you have been following the series, we are doing the complete DSA bootcamp, and this is a second video of the complete sorting series. So we'll be learning about so many sorting algorithms, comparing those, looking at the complexity and how what are the advantages, disadvantages, so on and so forth. So make sure you like, share and subscribe, and if you want to check out the previous videos, make sure you check out the link in the description. We have already done bubble sort, and now we're doing selection sort. So selection sort, basically, as the name suggests, you're going to selecting an element and you're going to sort that element. Like in simple terms, you're going to select an element and put it at its right position, put it at its correct position. Okay, so for example, I have an array like this. Selection sort. For example, I have an array like this, like put it to. So selection sort, basically, as the name suggests, you're going to selecting an element and you're going to sort that element. Like in simple terms, you're going to select an element and put it at its right position, put it at its correct position. Okay, so for example, I have an array like this. So, and I'm going to use selection sort. Selection sort is very simple, as the name suggests, like I mentioned already. Select an element and put it at its correct index. This can be done in two ways. Let's say you select the largest element in the array, then put it at its correct index. Then you select the second largest index from the remaining array, second largest element, put it at its correct index. For example, select the largest element. Which is the largest element from all of these? Which is the largest element? This one. I will select this and I will put it at its correct index, means over here. This will actually be swapped with this. Swapped. width becomes something like this. 5 is at the correct index. Now the remaining array equal to what? I would like to mention. Find the maximum minus, I'm going to say, okay, so this is what I want to swap it with, and I'm going to run a loop. I is equal to from start till end, start till end. Then I'm just going to say if array. We're already doing swap again and again, so let's create another function for swap also. So I'm going to say static int, I'm going to say int where object ref.
2 pointers, a powerful problem-solving pattern where you initialize two variables and move them towards each other, away from each other, or in the same direction based on the problem. There are currently 210 lead code problems tagged with this approach, which shows just how important it is for coding interviews. Using this approach, you can reduce the time complexity of many array and string related problems from order of n squared to order of n. In this video, I will break down what the two pointers pattern is, types of two pointers, when to use it, and I will walk you through multiple lead code problems to help you understand it better. I will also share a resource where you can practice more problems using this pattern. So let's jump in. What is the two pointers pattern? Let's first understand what a pointer is. A pointer is simply a variable that represents an index or position within a data structure, such as an array or linked list. Using pointers at different positions, we can efficiently compare elements and make decisions without relying on nested loops, which would otherwise lead to order of n squared time complexity. The two pointers technique can be applied in different ways, depending on the problem. Let's explore the three most common strategies. First, converging pointers. In this approach, pointers start at opposite ends of a data structure and move inward toward each other. The pointers adjust their positions based on comparisons until a certain condition is met or they cross each other. This strategy is ideal for problems where we need to compare elements from opposite ends of an array or a string. For example, checking if a string is a palindrome. A palindrome is a word, phrase or sequence that reads the same forward and backward. To check if a string is a palindrome, we initialize two pointers, one at the beginning and one at the end. Compare characters at both the pointers. If they match, move both pointers inward. If they don't match, return false. Repeat until the pointers meet. Next, parallel pointers. In this approach, both pointers start at the same end, usually the beginning, and move in the same direction. These pointers generally serve two different but complementary roles. The right pointer is used to explore or find new information, and the left pointer is used to track progress or maintain constraints. Sliding window technique is a popular variation of this approach. In sliding window, two pointers slide across an array or a string while maintaining a dynamic range. It's commonly used to find subarrays or substrings that meet specific criteria. I have covered sliding window in a separate video. Feel free to check it out if you want. And the last, trigger-based pointers. In this approach, we move the first pointer independently until it finds an element that meets a certain condition. After this, we start traversing with the second pointer to find additional information related to what the first pointer found. This technique is particularly useful when we need to process elements in stages. A good example of this approach is finding the nth node from the end of a linked list. We move the first pointer n steps forward. Once the first pointer reaches the nth node, initialize the second pointer at the head. Move both pointers one step at a time until the first pointer reaches the end. At this point, the second pointer will be at the nth node from the end. When to use the two pointers pattern? The two pointer algorithm is generally applied to linear data structures such as arrays, strings, or linked lists. A strong clue that a problem can be solved using the two pointers technique is if the input data follows a predictable pattern such as sorted array or palindromic string. For example, in a sorted array, moving a pointer to the right ensures you are always moving to a greater or equal value, making it easy to compare the values at both the pointers. Another strong indicator that a problem can be solved using two pointers is when it explicitly asks for a pair of values that satisfy a condition, or a result that can be generated from two values. Now let's walk through a few lead code problems to understand the two pointers pattern in action. If at any point you feel like pausing the video and trying out the problem yourself, feel free to do so. The first problem is lead code 283 moves. Move zeros. You are given an integer array, move all zeros to the end of it. You must do this in place without extra space and maintain the relative order of non-zero elements. For this input, the output would be a naive approach would be to create a new temporary array initialized with zeros. Then the output place without zeros. You are given an integer array, move all zeros to the end of it. You must do this in place without extra space and maintain the relative order of non-zero elements. For this input, the output would be a naive approach would be to create a new temporary array initialized with zeros. Then iterate through the original array and copy all non-zero elements to the new array. And finally, copy the temporary array to the original array. This works, but it takes extra space equal to the size of the input array. This violates one of the requirements since we have to do it in place. If instead of focusing on moving zeros, we can move all non-zero elements to the left, the zeros will naturally shift to the right. Therefore, we only need to focus on non-zero elements. We can use the two pointers approach to solve this. A right pointer scans the array to find non-zero elements, and a left pointer tracks where the next non-zero element should be placed. When the right pointer finds a non-zero element, we swap it with the element at the left pointer and move both pointers forward. Once the right pointer reaches the end, all zeros will end up at the right end of the array as intended, and all non-zero elements will remain in order. Here is how it looks like in code. Here I am using Java, but you can find the code for other popular programming languages in my GitHub repository called Awesome Lead Code Resources. You can find the link in the description. Start by initializing the left pointer to 0. It will be used to track and place non-zero elements. Iterate over the array using the right pointer to locate non-zero elements. If you find a non-zero element, swap the element at left and right pointer and increment the left pointer. The time complexity of this approach is order of n, since we iterate through the array only once. Height of a vertical line is the width of the container. A brute force approach to solve this involves comparing the area found by every possible
Hey everyone, today we're going to talk about a technique called sliding window. It's a very powerful technique and can significantly speed up some calculations. It's commonly used in algorithmic interview problems and sometimes in competitive programming contests as well. And in some cases it can speed up the calculations from quadratic to linear time complexity, which is a huge win and can make a big difference. It goes like of length k with the maximum sum out of all the subarrays of length k. This problem can be solved in many different ways, and one of the naive approaches that might come to mind is to iterate over all the endpoints of the subarray starting from k up to the very end of the array and compute the sum of each of those subarrays and finally extract the maximum out of those. In the case of this array, we would start from index 4 and compute the sum of the first 5 numbers, then move to index 5 and compute the sum of these 5 numbers, then move to index 6 and so on. So for each ending index, we would calculate the sum of k numbers and finally get the largest one out of those. As we calculate the sum of k numbers for each of the endpoints, the algorithm complexity would be O of n times k. Well, this is pretty slow, and we can notice that there are many redundant operations that can be eliminated. First of all, let's have a look at what exactly the algorithm does. For each endpoint, we iterate over all the previous k elements and sum them up together. Then move, and that the only actual change is the starting and ending coordinates. All the other elements stay the same. As we're interested in obtaining the largest sum, we can just subtract the element that left the current window of k elements and add the element that just entered it. So the new algorithm would start from the first k elements, then on each iteration we would move the endpoint of the current window to the right, add the new element and subtract the one that left the window, and repeat that process for all the endpoints from left to right. With this new algorithm, we would only perform one addition and one subtraction for each endpoint, and this makes sure that the algorithm performs all of n operations in total. Implementers and currency 13, 12, 16, and finally 11. Array has a sum of 18. This was a class can be do so by and then adjust the left pointer to make sure that the sum of the current window doesn't exceed 15. This makes it easy to implement the algorithm as we move the right pointer one step at a time while only adjusting the left one. Let's see the algorithm in action. We can initialize the left pointer to point to before the beginning of the array, initialize the current sum and the best answer to 0, and after that move the right pointer from the beginning of the array up to the very end, and on each iteration update the current sum and adjust the left pointer to make sure that the current sum is smaller than s. After adjusting the left pointer, we can update the current best answer as well. So for our example, initially the current sum would be 4, then 9, then 11, then again 11, then 12, then 20, so we'll start adjusting the left pointer. The sum will turn 16 and then 11. After that, we'll update the right pointer again and the sum will become 23. So we'll adjust the left pointer and the sum will first
हैशिंग टेक्निक क्यों इसको इस्तेमाल किया जाता है और आपके लिए ये किस तरह कारगर साबित हो सकती है। तो हैशिंग की अगर हम बात करें क्या होती है हैशिंग, हैशिंग इज़ अ टेक्निक टू कन्वर्ट अ रेंज ऑफ की वैल्यूज़ इनटू रेंज ऑफ इंडिसेस। तो मैं यहाँ पर जल्दी से लिख देता हूँ इस बात को, टेक्स इंडिसेस में स्टोर किए जाएंगे, ठीक है। तो ये बात जो है हैशिंग टेक्निक हमें बताती है। मान लो यहाँ पर एक एरे है, मैं इसको एक्सप्लेन करता हूँ इस बात को जो मैंने बोली यहाँ पर देखो 3 4 5 6 7 8 और 9। मान लो यहाँ पर ये हमारा एरे है, इस एरे का साइज़ 10 है जैसे कि आप लोग देख सकते हो। अब मैं यहाँ पर करूँगा क्या, मैं चाहता हूँ इसमें कुछ नंबर्स को ऐड करना। तो मेरे पास दो तरीके हैं, या तो मैं क्या करूँ कि सिंपली यहाँ से ऐड करना शुरू कर दूँ। मैं यहाँ पर लेटर से मुझे नंबर स्टार्ट करना है 72, उसके बाद 39, फिर 11, ठीक है, फिर 18। ये सारे नंबर्स मान लो मुझे इंसर्ट करने हैं, या तो मैं इस एंड से इंसर्ट करना स्टार्ट कर दूँ, ठीक है, जैसे कि हम करते हैं इंसर्शन इन एरे, हमने देख रखा है ऑलरेडी। अगर मेरे एरे का साइज़ 1 लाख है तो मुझे 1 लाख कीज से गुजरना पड़ सकता है अपने एलिमेंट को सर्च करने कर पाऊँ। ये काम करूँगा ताकि यार आप लोग को देखे। अब 39 को मैं 9 पे स्टोर कर दूंगा, ठीक है, यहाँ पर मैं 39 को स्टोर कर दूंगा और 11 को मैं कहाँ पर स्टोर कर